Up here our chapter we've been on, which is about solutions, I think. So obviously we've been talking about solutions. And really, as of late here, we've been talking about really concentration, things like molarity, which is our moles per liter. We also talked about dilutions. And when we do a dilution, remember that basically we are just adding more solvent. And in a lot of cases, that solvent can be water, but it can be other things as well. And the result of sort of adding more solvent is when we look at molarity, it is moles of the solute over liters of the solution. And really, when we do that sort of addition of more solvent, really the only thing we're sort of adding to in this case is the liters of solution part, which means that number gets larger, the molarity comes down, which is the whole point of really the dilution. In terms of what stays the same when we do a dilution, it is the moles of the solute remain the same, as we're just really changing the solvent. So most of the time people use M1V1 equals M2V2. Again, there's more of a generic version of this equation, which uses C1V1 equals C2V2, where C is just a generic concentration type unit. Although molarity is the most common concentration unit, that's why most people will use M1V1 equals M2V2. You can use any really concentration unit in there, which is why the C is there. So you can use something like percent mass to mass, percent mass to volume, and so forth. We sort of put this together and talked about stoichiometry that involves solutions. And when we're doing stoichiometry that involves solutions, the good news is it's really just sort of the same steps that we've done before in stoichiometry problems, be it a basic stoichiometry problem or a limiting reagent problem. It is basically still you're going to balance your equation. You're going to convert to moles. Remember that if you do have enough information to get to the moles of each of the reactants, you do need to do that limiting reagent step there and determine which one is the limiting reagent. Obviously, if you do not have enough information to get to the moles of each reactant, then it's a basic stoichiometry problem, so you don't have to worry about obviously that step. That step is you could use a calculation obviously between the two reactants and figure out, do you have enough to use up one of the reactants with the other reactant in terms of what you're starting with. Once you figure out which one is the limiting reagent, if necessary, then you would do the mole to mole relationship between the two things you're interested in. And obviously, if it's not a limiting reagent problem, you just go right to the mole to mole step. And lastly here, you'll convert those moles obviously into some other unit. So really the main difference in terms of how we work these problems, a lot of it revolves around sort of the second step. So instead of using grams to moles, we very often use moles is liters times molarity. To get to the moles is a very common sort of variation. And the other place is at the end of the problem, we could still do our normal, in a lot of cases, moles to grams using the molar mass from the periodic table to do that. But in other cases, we may take those moles and maybe we're giving a volume and we could use that to get to the molarity. We could also take the moles and maybe we are given the molarity, which means we could get to a volume. So at the end of that sort of calculation, there's a few options as to sort of how you could finish up the problem. And those are usually one of the three sort of options here. Any questions on any of that stuff we talked about last time? All right, so to finish up sort of talking about solution stoichiometry, we're going to talk about a specific type of stoichiometry, which involves neutralization reactions. And these are typically acid-base type reactions. And if you remember, when you take an acid and you react it with a base, you do get basically two things. You get salt and water that is formed. And really, when we look at a strong acid, strong base combination, as I think we talked about when we did types of reactions, no matter what combination of strong acid, strong base, for example, if you took hydrochloric acid plus some sodium hydroxide here, you will get some sodium chloride and some water. By the way, the H from the acid and the OH from the strong base is where that water always comes from. And basically the salt is just the other two guys coming together. It is a double displacement reaction, as we've talked about before. If we were to write our total ionic equation for this, this would be H plus and Cl minus from our hydrochloric acid, as is a strong electrolyte and break apart. Sodium hydroxide being a strong base will also break apart. Sodium chloride is a strong electrolyte and an ionic compound that will break apart. And our water will stay together as it is a liquid. A reminder that we keep together anything that is a liquid, a solid, or like a gas or a weak electrolyte. Our spectator ions in this case, sodium and chloride on both sides, they completely cancel out. And again, we are left with the overall reaction that we see on the screen here. What always occurs when we take a strong acid with a strong base, it really is just a formation of water that's sort of happening here, which is why they are called acid-base neutralization reactions. It is also one of the three driving forces for a chemical reaction that we talked about, right? The three driving forces for a reaction is electrons being transferred, a solid being formed, and water being formed. So it's one of the reasons why a reaction basically takes place. So oftentimes in a lab like you did on Monday, like you will do today, oftentimes we do perform these sort of neutralization reactions through a process known as titration, which is a very common sort of method to sort of do this acid-base reaction. So in a titration, we again usually will add a known solution to an unknown solution. And what I mean by a known solution is, we know something about the molarity of it. We know really the volume of it. And maybe for the unknown, all we know is the volume, or, maybe we even know the molarity of it, what it might be as well. But a lot of times you'll just kind of know the volume in most cases. And as you did on Monday, and we'll do again today, usually when we do a titration, again, we use a burette. And for example, you could put your base up in the burette. You could also put your acid up there if you're doing a different type of titration. It doesn't really matter. But in most cases, the base will be in the burette. And in the beaker or the flask would be, for example, your acid. And the idea here is, for example, like the experiment that we did, the molarity of your base. Here, the volume of the acid that you're adding or that you're starting with. We also include, obviously, like you did, an indicator. And an indicator, again, will change color near the equivalence point in a titration. And again, the equivalence point in a titration of an acid and a base is the point where the moles of the acid will equal basically the moles of the base. So it is that exact point where pretty much you've neutralized each other. You've added enough base to neutralize all the acid you started with in a titration. Ideally, if you pick an indicator, it should change color near where that is occurring to give you a visual representation that you should stop your titration because you're pretty much there. So for example, the one that we use and very commonly used in a lot of places is phenolphthalein. Spell that 3 times. And again, it does work over a pH range. So again, phenolphthalein works at a pH range of like 8.3 to about 10-ish. By the way, that is basic. That's above a pH of 7, which means it actually works in the basic range. It is colorless in acidic solution, is colorless in neutral solutions, and truthfully, it's colorless around 8.3. Right a little bit after that, you start to get not red, but obviously you get that pink color that occurs from light pink to kind of dark fuchsia, nice color pink at the end of that scale. And again, we pick something like this because ideally it is around where the equivalence point should be. It's probably a better choice for the titration we're doing today. The one we did yesterday, it works okay. But the reason everybody yells at you to get the lightest color pink that you could see is because that really should put you in terms of the pH around where the equivalence point should be. If you get really dark color pink, you may be past the equivalence point. So as many of you maybe said to yourself or saw when you were doing the titration, you might have saw like, hey, I just added like 1 drop and it went from like kind of like no color to really a darker sort of color pink. And the reason for that is you'll learn in 1B, if you take 1B, we look at something, what is referred to as a titration curve, which is the entire curve of what's happening when you do a titration and say the volume of base added. And titrations like the ones we did on Monday and today will typically look something like this, sort of an S shape, where the equivalence point is, say, right about there. Right. Now, what happens as you approach the equivalence point, what you might have also saw as you're doing the titrations is at some point the pink kind of stays a little bit longer and then it goes away, kind of stays a little bit longer, goes away. And that means you're kind of approaching the equivalence point. So as you start to titrate, you're moving. And then as you get towards the equivalence point, you oftentimes will see sort of a big jump in the pH to the equivalence point. And then if you go past the equivalence point, you will also see a relatively big jump in pH. The problem is as you approach the equivalence point, this line is pretty vertical, right? Which means, does it take a lot of volume to change the pH? A lot. It does not, right? So you could be about here, or you could be about here. And in terms of volume, it's like pretty much the same spot, right? Which is like 1 drop, 2 drops, something like that. So although you may be close to the equivalence point, when you add that 1 drop or 2 drops, it will change the pH a lot, which means in terms of my indicator, I may actually be finding myself way over here in the indicator range, which will give you that lovely dark pink color, right? In the end, does it really matter if I miss it by a drop or 2 in terms of the volume? It's pretty much the same, no matter where you are. So it really doesn't matter, which is why sort of the volume is really important. But it could definitely matter if you were not careful. So if you titrated like me, where you just opened it up, let it all drain, shut it, and it's like dark pink and you left, you really weren't very careful about how you're adding the titration, which means you could also hit dark pink and be like way over here, right? Because that's also about the same pH, right? Which means it's going to be super dark pink as well over there. And now, did I miss my equivalence point by a lot of volume? I did, right? So that's why usually teachers are like, oh, you want the lightest color pink that you could get, so they know you didn't like super jump over the equivalence point. But really, if you're careful and you miss it by a drop or 2, you know, it doesn't really make a big difference in terms of the calculation because the volume is going to be roughly the same. But again, if you weren't very careful as you approach the equivalence point, you really could find yourself with the same color, but very, very far away. So in future titrations that you do, just be careful, go slow. And again, don't be so hung up on the color. Again, it's more important oftentimes when you do a titration that the volume of, say, sodium hydroxide or base or whatever you're adding is about equivalent with each other every time you do the titration, rather than maybe necessarily the color. Sometimes people put a little bit too much emphasis on the color, and it can jump a lot just from a drop or 2. Any questions on that? So again, that is the age-old question of I just added 1 drop and went super pink. That is, again, why it does that, because basically you have a very big change of pH with a very small volume, which makes your indicator go crazy in terms of its color. All right. So when we do a titration, obviously the goal is to stop there at the equivalence point. Sometimes you also hear the term endpoint in the titration. And the endpoint is pretty much what it sounds like. It's pretty much where you ended your titration. So it's kind of like where you laid it up. In a really good titration, your endpoint and your equivalence point should hopefully be very close to each other. You should hopefully stop near the equivalence point in most titrations that you do, except when you do go to 1B, you will continue past the equivalence point and do the entire titration curve. But most of the time, you want to stop there at that equivalence point. So when you do stop and the reaction is done, what you will typically know, for example, is the volume, right, of your base that you added. So really you'll have the molarity and the volume of the base you added, which means if you take both of those things together, you can get the moles of the base. You then could do some stoichiometry to go from moles of base to moles of the acid using the balanced equation. And from that information, you will be able to get, say, the moles of the acid that you started with, which is really good because then you'll have the moles of the acid. You'll also have the volume of the acid that you started with, which means you could calculate the molarity of your acid, which again is a common sort of thing that we do, obviously, in titrations. Any questions on that there? All right, now again, sometimes you may not be calculating molarity at the end. Maybe you'll be calculating volume or something like that. But a lot of times molarity or volume is two things that you oftentimes are looking for. And these type of problems, they really are just the same solution stoichiometry problems that we've done before. And a lot of times in a titration problem, because there's an unknown solution, they're basic stoichiometry problems, basically, where you just kind of use the volume and the molarity there to get the moles. You don't have to worry about limiting reagents in a lot of cases because you don't have enough information to get moles of everybody. So why don't we try one here? What volume of 0.15 molar nitric acid is needed to neutralize 45 milliliters of 0.55 molar potassium hydroxide? So why don't you approach it like a problem here? Is really a titration problem. So see what you come up with here. So it is really also a stoichiometry problem. So some equations, some moles, give it a go. Problem really is still a stoichiometry problem. So really you want to start with our 4 steps, which is we want to balance the equations. So in this case, we have a strong acid, which is nitric acid, plus potassium hydroxide, which is a strong base. Again, it really is a double displacement reaction. And really one of the products there should be water, and our salt will come from the potassium and the nitrate coming together. And potassium is +1. Nitrate there is -1. So that's going to give us KNO3 in this particular case. We want to obviously make sure that it is balanced. And I think in this case, it is balanced. We got 1 NO3 on both sides, 1 potassium. We got an extra oxygen and 2 hydrogens. So I think we are good in terms of that. Next thing we want to think about what is sort of given to us. We are looking for the volume here of this guy. We do have the molarity. We also have the molarity and the volume of our KOH. So in this particular case, it is a basic stoichiometry problem, as this is the only one that we could get moles from, clearly, because we're looking for a volume here. We cannot get the moles of that guy. So really, all we have to do next is convert to moles. And again, this is the major difference, which is we're going to use the volume and the molarity to do that. We do want to do a couple of conversions here, perhaps. We do need, again, always when we're using molarity and volume together, it needs to be in liters. So we need to take our 45 milliliters. We'll divide it by 1,000 milliliters is a liter. Will give us 0.045 liters of our KOH. We're going to turn this guy into really like a conversion factor, which means 0.55 moles per liter. Or again, if you needed to, you could flip it around the other way and do the moles on the bottom. In this case, we actually need it just like it is there on the left. So using the molarity here of our base, 0.55 moles per liter of KOH, the liters will cancel, and that will get us 0.045 times 0.55. Going to give us 0.2, oops, got 0.02475 moles of the KOH in this case. Now that is moles of KOH, which is really not what we need in this case, because ultimately we're looking for the volume here of HNO3. And if we think about molarity, we are looking for this guy. We obviously have the molarity of the acid. So to finish it out and really calculate the volume of the acid, we do need the moles of the acid, not the moles of the base. So this is where the stoichiometry part comes into play. We can see from the equation here, the mole-to-mole relationship happens to be, in this case, a 1-to-1 relationship between those two, which means we can use that to convert from moles of our base into moles of our acid by using stoichiometry, which is really like the third step that we typically do. So in this case, 1 mole of KOH will equal 1 mole of HNO3. And that's going to give us 0.02475 moles of nitric acid in this case. Any questions on that there? Now that we actually have the moles of the nitric acid, we now have the moles, we still have the molarity. So we could rearrange the molarity equation here and solve for volume. And the volume in this case, liters, would equal our moles divided by our molarity. So to do that, we're going to take the moles that we just got. We're going to use the molarity of the acid that was given to us. We're also going to get rid of the big M and use both of the units. And in this case, we need to flip it upside down so that the moles cancel. So 0.15 moles per liter of our nitric acid. The moles of the nitric acid will now cancel in this case. And that will get us divided by 0.150. 0.165 liters of nitric acid is needed, which if we multiply by 1,000 will tell us that that is 165 milliliters of nitric acid is needed. So if this was a titration, you would need to add about 165 milliliters of nitric acid to reach the equivalence point when you started with your 45 milliliters of the potassium hydroxide. Question on that. So it really is, yeah. Yeah, I'm gonna say, so I'll put the, you really shouldn't use that one because it really should be used for a dilution. It will work out right in a 1-to-1 relationship, but if your stoichiometry is not a 1-to-1 relationship, you'll be off because you don't have the right stoichiometry part of it. So I would highly recommend not to do that. And sometimes people even call that, sometimes if you look online, they'll call it like the titration equation as well. But it really does only work specifically for when you're doing a titration that the mole-to-mole relationship between the acid and the base is 1-to-1. It will be off, obviously, if it's not. So it's best not to do it for that and just use it for dilution and do more of a stoichiometry approach for titration problems. Yeah. Other questions? So specifically for this class, you got to show that work, not the M1V1 equals M2V2 type stuff. Yeah. Okay. Other questions on that? All right, let's take a look at another one. I think you have one, so we'll do that one first, which is, I don't know where mine went, but I believe what you have on your notes is, what is the volume of 0.5 0.5 molar sodium hydroxide is required to react with 125 milliliters of 0.5 molar sulfuric acid. All right. So give that one a go, see what you come up with. Okay, let's take a look. So once again, we really have sort of a titration type problem here. So we're going to start with our equation. In this case, we got sulfuric acid reacting with some sodium hydroxide. Once again, going to basically switch partners here, and a result of that will be water being formed. Once you basically take the water out of there, what's left is the sodium and the sulfate that will come together, and that wants to be put together correctly, which means we will need 2 of the sodiums to go with 1 of the sulfate in this case. At this point, we do need to do some balancing here, which I think we need a 2 there and perhaps a 2 there, I think, as well. And now I think we should be good. Any questions on that? All right, so kind of the same idea here. We have a balanced equation. We want to look at it. And in this particular case, we are looking for the volume here of the sodium hydroxide. We have the molarity given to us. So once again, looking at molarity, we are really missing moles here to allow us to do that, as this is what we're looking for. So to do that and to kind of get there, we're going to use stoichiometry, and really in this case, the volume and molarity of our acid, because we do have that given to us, which is 125 milliliters and 0.5 molar, which means we can get moles from that guy. So that is what we're going to do. We are going to convert, once again, our milliliters into liters. So 125 milliliters, 1,000 milliliters is a liter, gives us 0.125 liters there of our H2SO4, using the molarity so that the liters cancel, which means the moles should go up on top. Liters on the bottom of our H2SO4, the liters here will cancel. In this case, we end up then with 0.125 times 0.5 gets us a 0.0625 moles of H2SO4. Once again, though, we do need the moles of the sodium hydroxide to figure out what we're really looking for. So that again is where the stoichiometry comes into play. And in this case, unlike the last one, right, we actually have a 1-to-2 relationship between those two. So we do have a different mole-to-mole relationship. And to do that, then we will use it to convert to what we need. In this case, looks like we're going to go 1 mole of our H2SO4 on the bottom, 2 moles of sodium hydroxide up on top. The moles will cancel, and that's going to give us 0.125. We got there. Moles of sodium hydroxide. Now that we have the 0.125 moles of sodium hydroxide, we now have obviously the moles. We still have the molarity. So much like we did last time, we can now solve for the liters, which would be our moles divided by our molarity. So using our moles of sodium hydroxide, here we're going to use our molarity with the moles on the bottom of the sodium hydroxide. So that's going to be 0.5 moles per liter. Moles will cancel, and we'll take that divided by 0.5. And that will get us 0.25 liters of sodium hydroxide, which again, if we times it by 1,000, we'll turn it into milliliters, or about 250 milliliters of sodium hydroxide in this particular case. Question on that there. So to answer sort of the earlier question, if you did use that M1V1 equals M2V2 here, you would get 125 rather than the twice as much that you need, which is actually 250 in this case. So again, make sure you do it more of a stoichiometry problem if it is a titration, and use that kind of other one for more of a dilution type of situation. Question on that there. All right, let's try one more here to finish up here. Let me try this. Let's say it required 37.5 milliliters of 0.352 molar calcium hydroxide to reach the equivalence point of we'll do 55.5 milliliters of hydrochloric acid. What is the molarity of the HCl? All right, so take a moment, see what you come up with. I'll do it as well since I just made up numbers. We'll hope for the best here and see how we do. Okay, let's take a look at this one here. So this again is titration problem. In this case, though, we are looking for something a little bit different. We're looking for the molarity at the end, but really the rest of the calculation is pretty much the same. So we'll do our equation, which is our hydrochloric acid plus our base of calcium hydroxide here. And again, we're just going to do sort of our double displacement, and our water is going to come from those two spots right there, basically. So that'll give us our water. And again, we want to put our calcium and our chloride together correctly. Again, calcium being +2, Cl being -1. So that should give us a CaCl2 going on. That means we probably need to do a little balancing here. So a 2 there and perhaps a 2 there, I think. And we hopefully should be balanced at that point. Any questions on that there? So at this point here, we are looking for the molarity of the HCl. We do have the volume given to us of 55.5 milliliters. In terms of the calcium hydroxide, we do have obviously the volume of 37.5 milliliters, and we have the molarity given to us, which is 0.352 molar. That means obviously from the two pieces of information, we could get the moles of our base, and that's helpful since we are looking for the molarity of our acid. We actually already have the bottom part. We just need to do a conversion. So basically we need the top part, which is the moles of the acid, and that's going to come from the stoichiometry part of the calculation. So we will convert to moles, which is the only thing that we can convert to moles of, which is our calcium hydroxide. Once again, we're going to divide our 37.5 milliliters by 1,000 to convert that again into the right unit that we need, which is liters. Always want liters with molarity by itself, 0.0375 liters. We now can use the molarity of our base, again, getting rid of the big M, using it more as a conversion factor. So we're going to put the moles up on top, liters on the bottom of our calcium hydroxide here. Liters will cancel. This will get us, looks like 0.0375 times 0.352 gets us a 0.0132 moles of calcium hydroxide. Any questions so far? So kind of like a basic stoichiometry steps. Major difference again is not using the molar mass in grams, but using volume and molarity here. Now we need to get to our HCl. So again, using the balance equation, we could see, not that, we could see a scribble apparently. Let's not do that there. Let's get rid of that. There we go. So we could see it is a 2 to, where we go in there? 1 relationship there. So it's a 2 to 1 relationship between those two guys. So for every 2 moles of our HCl, we get 1 mole of our calcium hydroxide. And that's what's going to allow us to get to the moles of HCl, which is really what we need to finish this calculation. So we'll go 0.0132 moles of calcium hydroxide using our mole to mole relationship from the balanced equation. 1 mole of calcium hydroxide gets us 2 moles of HCl. Moles of calcium hydroxide will cancel. We'll take that times it by 2. Going to give us 0.0264 moles of HCl. So by doing the stoichiometry part here, we now have the moles of HCl that we need. So the variance here is, instead of step 4, where we maybe figure out volume like we did previously, or we figure out grams using the molar mass, we're actually just going to calculate the molarity at this point. So we could calculate the molarity of the HCl by taking the moles we just calculated, 0.0264 moles, divided by the liters of this. So once again, we still need to do a conversion to get that into liters. We do not want to divide by milliliters. So again, 55.5 milliliters, 1,000 milliliters in a liter, 0.0555 liters. That is what we want to make sure we're dividing by. And if we do that there, then looks like a 0.476 moles per liter of HCl. Or again, you could write 0.476 big M HCl, whichever way you would like to do that. Any questions on that? So hopefully you can see that really titration problems are really just stoichiometry problems, and they're really just solution stoichiometry problems where basically you kind of just use molarity and volume. Any questions on any of that stuff there? That wraps up chapter 15, is it?